Alright, now it's time to look at a pretty challenging problem involving tree recursion. And I know I just introduced the concept of tree recursion, but I think with this example you'll see really why recursion is so great and helps us solve these problems. So what we have to do in this problem is we want to write a function, count partition, that takes in two arguments, n and m, which are both positive, or more specifically non-negative integers, and it returns a number of ways. A number n can be partitioned using parts up to m. So for example, count partition on 5 and 3 would give us the following partitions. And what we want to return is 5 because there are 5 partitions. So to get a more visual look at this, here is a visualization of the partitions. So here we have 5 is equal to 2 plus 3. So here's our partition 2 plus 3, 1 plus 1 plus 3, 1 plus 2 plus 2, and all of these add up to 5. And then if you want one more example of exactly how this works, here's a count partition of 6 using parts up to 4. So notice that we're not using any parts up to 3, which is the definition of the problem. Alright, so now my big challenge of the day, and I don't expect you to actually get this because I don't think many 61A students were able to get this one, but how can we solve this problem by splitting up into simpler problems and finding a recursive way to go through this and build up to the final solution? So if I want to take in these inputs and find a way to get 5 basically, and what sub-problems should I basically solve? That's the essential question here. And this is a very, very challenging problem, but take some time to really think about it. And if you really, really want to go deep into it, it might take an hour to even figure this out. So anyway, I'm going to spoil the solution in 3, 2, 1. So solving this count partition problem really forces us to look at two fundamental possibilities. When we have a count partition of n with parts up to m, at the end of the day, our solution is either going to use at least one m, or it's not going to use m at all. So to look at a specific example, if we want to count the partition of 6 using parts up to 4, there are really two simpler problems. It's either we count the partition of 2 using parts up to 4. Why 2? Well, this is the case where we use at least one m. And if we use one m, well, what do we have left? We have 2, because 6 minus 4 is 2. So then we have to ask how many ways can we partition 2 using parts up to 4. And another thing the other simpler problem we have is that we don't use m. What happens if we're not allowed to use m? Well, then it's really just asking, hey, what's the next largest number I can use to partition 6? And the next largest number of that is 3. So these are the two simpler problems that we can split up. And again, tree recursion is all about, these complex examples of tree recursion at least, are all about finding decisions. It's basically about making decisions. Like, should I use this one? It's evaluating choices. So in this case, we're looking at, hey, I can either use an m or I don't use an m. So that's what tree recursion is very good at doing. And here's the example with count partition 5 and 3. So this is all pretty abstract, and I get that. It's kind of hard to understand. When I first saw this, I was like, whoa, what the heck is that supposed to mean? So let's look a little bit at a visualization of exactly how this works. So if I want to count partition of 5 using parts up to 3, my first choice is I can use a 3, or at least one 3. So what are the choices that use at least one 3? Well, only the first two. So now, what is the solution to this problem? Well, it's really the ways to count partitions of 2 using parts up to 3. So here, once I use a 3, I only have 2 left. And then at the end of the day, the solution to this smaller problem, focusing only on this problem, is the partition of 2 and then 1 plus 1. And that's the ways to partition 2 using parts up to 3. So this is the key idea here. And then if I don't use 3, I have the rest. So none of these solutions to this problem use 3. They only use parts up to 2, but they partition 5. And this is the key idea in this problem, seeing this pattern. And let me go through it one more time just so we get it clear. It is a little hard to see. So in this case, when we want to count partitions of 6 up to 4, well, we only have 2 4s. And then this ends up being very similar to this, count partition of 2 using parts up to 4. And then what's our next case? That we don't use a 4. So now we have all these possibilities, 7 of them to be precise. And now, remember, recursion keeps on going until a base case. I'm not going to go all the way to the base case, but if we go further into this problem, the count partition of 6 and 3, then we ask ourselves, hey, we can use a 3 or we don't use a 3. The possibilities where we use a 3 are the following. So this is, in reality, just count partition of 3 using parts up to 3, because now once we've used a 3, we only have 3 left. And these all just involve partitioning this 3 into either 3, 1 plus 2, or 1 plus 1 plus 1. So that's how we get the solution to that. And then, with this, well, this is just a ways to partition 6 using parts up to 2, because now we're not allowed to use either 4 or 3. So now this is how we slowly converge into a solution to the problem, and at the end, we have base cases and we converge everything back up to get our solution. And once we figure this out, the actual solution to this problem is not too bad. So let's take a look at that. So I've defined this count partition function. I've put our tests in. And now, let's just think about this. Again, we have 2 possibilities. We either use m, or at least one m to be more precise. It could be the case that we use more than one m. But if we use m, then what happens? That means we have n minus m left, and we have to partition that using parts up to m. Okay, so this might be a little confusing, but so basically, let's go back to our example. Once we've used a 4 here, what are we partitioning then? We're partitioning 6 minus 4, which is 2. So that's the key idea here. And then if we don't use m, we basically are partitioning the same number, but we have to use the next largest m. Next largest number that's as close to m as possible, and that's just m minus 1. So now, once we know this, writing the code is actually quite natural. So the first thing we do, of course, is think about the base cases. So when you're thinking about base cases to these type of problems, always ask yourself, hey, what's the simplest version of the problem I can think of? Well, I can think of a few simple versions of this problem. What if I had nothing to partition? So my n is equal to 0. Well, how many ways can I partition 0? Well, it turns out there's just one, nothing. So that way, I return 1 partition of 0. Now, what if, so remember, we're working with non-negative integers. So what if I actually end up getting, because I am subtracting some stuff here, what if I end up with a negative number? What does that mean? Well, ask yourself, how many ways can I partition a negative number? Well, since we're only working with non-negative numbers, that would be 0. So here, we're going to return 0. And then, the next problem I'm going to be working on is with m. What if we have nothing to partition up to? We can only partition up to 0. What does that mean? Well, ask yourself this. How many ways can I partition 1 using parts up to 0? Well, obviously that doesn't make any sense. You can't partition 1 unless you have a 1. So this would return 0. And now, here we have our tree recursive case, because this is all the base cases. And I guess a question that might arise is how do you know you're done with base cases? Well, there's really no good way, but you have to just basically think of what are the simplest versions I can think of, and if there's nothing else, you could have extra base cases. That's fine. It won't change anything. So like I could have if n is equal to 1 and my m is equal to 1, I could have just 1 because I know there's only one partition of that. But that's a little redundant because these fundamental base cases handle that. Alright, so what's our first choice? We can do with m. And how many ways can we partition that? Well, that's just a matter of partitioning n minus m, with using parts up to m. Because once we've used m, we have to subtract that from our total n. Again, this is kind of like the reverse of addition. Remember, we're adding things together to get a partition. So to undo that, using something means we're subtracting it from the total. Alright, and then we also have without m as a choice. And how many ways can we do that? Well, that's just to count partitions of n using the next largest number, which is m minus 1. Because if we can't, for example, if we can't use 4, then we can only partition 6 using parts up to 3, and so on. And then at the end of the day, our solution is just with m plus without m. And so now, let's test this. And it works. So this is count partitions. And here is the implementation of it. So again, one thing to notice is that, remember, this problem seemed like quite a monster when we first saw it, right? Like, how would we figure this out? But turns out with tree recursion, the solution is less than 10 lines. So that's pretty, this is why tree recursion is so awesome. The iterative version of this solution would be much more complicated and requires a lot more just nasty code, I think, in my opinion. Whereas this is very, very elegant, and I just really like this implementation. It's very clever. Now, before I end this video, I also want to point out a few things. I'll talk a little bit about why recursion is important, and also I want to throughout this entire course series, I've been heavily relying on CS61A material, and some of it's a little different because it's my own interpretation, but in this lecture, this is actually mostly straight from John Denaro's lecture slides and also the Composing Programs textbook, so I encourage you to look at those resources too. I go a little bit more into detail on this because I think this is quite a confusing topic when you first look at it. So, but I do want to know that this definitely wouldn't be possible unless the CS61A course staff, as great as they are, didn't come up with this. So good for them. This course is amazing. CS61A overall is just an amazing course, and I have to give them credit where credit is due. So thanks CS61A, and I haven't been saying that enough, but thank you, really. CS61A is an awesome course, and it does a great job of preparing people for the computer science life, basically.